Have you ever stopped to wonder what actually happens when a massive underwater internet cable gets severed, but your streaming video doesn't even buffer? It's crazy, right? Well, welcome to this explainer. Today, we're decoding the invisible nervous system of the internet. Using the CCNA official cert guide, we're going to dive deep into OSPF. That's the hidden, elegant math keeping our entire digital world connected.
So let's start with Section 1, the Internet's GPS problem. Think about the massive logistical nightmare of moving data across the globe. When a cable gets cut or a switch just completely dies, how does a network adapt instantly without you ever noticing? I mean, how do routers sitting in cold server rooms miles apart from each other collectively agree on the absolute best detour in fractions of a second? Well, to wrap our heads around this, think of IP routing just like the global postal service. In this model, IP addresses are the unique houses, apartments, and businesses. And the routers? They're the post offices moving the mail. Just like the Postal Service had to build this massive infrastructure of sorting machines, trucks, and planes, the network layer defines exactly how routers forward digital packets of data so they are delivered perfectly to the right destination. But how do they actually choose the best route? In the early days, we relied on distance vector protocols like RIP, and RIP just counted the hops, literally just the number of routers in the way. It's kind of like your GPS blindly telling you to take a one-lane dirt road just because it's technically a shorter distance. No thanks. OSPF, on the other hand, calculates the actual cost based on link bandwidth. It automatically finds the multi-lane highway for you, completely ignoring those slower, shorter back roads. It's a real game changer. Which brings us to Section 2, meeting the router neighbors.
Because before routers can calculate those high-speed routes, they got to make some friends first. Down in the hardware racks, these routers are connected by tangible Ethernet and serial cables. And they need a highly structured way to introduce themselves over these very physical wires before any digital routing can actually happen.
It's just like moving to a new neighborhood, right? You don't just start shouting your entire life story on day one. First, a router sends a hello packet out of its interface. This is the init state. When the neighboring router sees it and replies with its own router ID, they reach a two-way state. They literally see each other. Finally, if all their configuration parameters match perfectly, they agree to exchange all their information, moving into a full state. Boom, new best friends.
But here's the big question. Once they say hello, how do they actually share the map of the entire network? Knowing your neighbor is great. You can wave across the fence. But getting the actual detailed directions to everywhere else in the enterprise network, well, that is where the real magic of a link state routing protocol happens.
Let's explore that in Section 3, building the topology map. To build that God's eye view of the entire network, OSPF breaks things down. Each router creates something called a link state advertisement, or LSA. You can think of an LSA as literally just one piece of a giant jigsaw puzzle. It strictly describes the router itself, its local interfaces, and the status of its direct links. By continuously flooding these individual LSAs to all their neighbors, who then immediately reflood them to their neighbors, every single router eventually gets all the puzzle pieces. When assembled, this is called the Link State Database, or LSDB. And the result? Every single router in the network has a completed, perfectly identical jigsaw puzzle sitting right there in its memory. So if every router has the exact same giant puzzle, how do they calculate the single fastest path? Having the map is one thing for sure, but if you have a massive enterprise network, calculating the absolutely fastest route from your specific location through that entire map requires some serious heavy lifting. This is where we get to Section 4, calculating the fastest route. This is where OSPF moves from just knowing the map to actively charting the course. The CCNA text has a totally great line about this. It says, to build routes, link state routers have to do some math. Thankfully, you and I do not have to know the math. And it's so true. Under the hood, they use this intense Dijkstra shortest path first algorithm to find the absolute least cost route to every single destination. But for us, it just comes down to simple addition based on bandwidth. OSPF uses a reference bandwidth to automatically assign a cost to a link. Fast links, like a 10 gigabit connection, get a super low cost, like 1. Slower 100 megabit links get a higher cost, like 100. The router simply adds up the numbers across the entire path and picks the route with the lowest total score. It's exactly like golf. The lowest score wins. And this method is mathematically guaranteed to find the fastest way. But wait, here is the catch. What if the puzzle gets too big? Running that complex Dijkstra math on a database of 1,000 routers would absolutely crush a router's CPU and memory, causing massive slow convergence and network log. Obviously, we can't have that. So OSPF has a brilliant way to scale up. Let's check out Section 5, Scaling Up with Areas. To prevent those nasty CPU meltdowns, OSPF uses a structured hierarchy. It breaks the massive network into smaller areas. Instead of one giant, overwhelming puzzle, you have smaller, manageable puzzles. Routers only need the highly detailed pieces for their specific local area. They just rely on area border routers for simple, summarized directions to the rest of the network via the central backbone, which is known as Area 0. Problem solved. Well, mostly solved. Because even within one area, things can definitely get out of hand. Imagine you have 20 routers all plugged into a single Ethernet switch, like some of the massive enterprise cabling setups out there. If they all tried to become fully adjacent neighbors and all shouted their database updates at every single other router simultaneously, it would cause absolute, complete chaos on the local network. Which leads us to our final part, Section 6, the elegant math of routing. To solve this local traffic jam, OSPF doesn't let everyone talk to everyone. Instead, it actually holds an election. Routers on a shared link choose a designated router, or DR, to act as the network boss, and a backup DR just in case things go south. All the rest become deauthors, which means they only fully sync up with the bosses. The bosses then efficiently broadcast the updates to everyone else using dedicated multicast IP addresses. It cuts down network traffic exponentially. It is incredibly clever. When you put all these pieces together, you get the final picture. Just look at how cleanly organized a well-built physical infrastructure is. OSPF is simply the digital equivalent of that organization. From saying hello to building the puzzle database to electing network bosses, OSPF is an elegantly choreographed dance, routing around failures in mere milliseconds. So next time you stream a video, ask yourself, how many OSPF neighbors just shook hands to make it happen? It is a fascinating, totally invisible world operating right under our fingertips every second of every single day. Every click, every stream, every message relies on these routers doing their complex math and shaking hands behind the scenes. Thanks so much for joining me on this deep dive into the hidden logic of the internet. Until next time, keep questioning how the digital world really works.